the idea is for us to get started in the space of generative AI. And then one of the major breakthroughs in the generative AI was when a company called Stability AI, in partnership with a couple of other organizations, made this model publicly available, which is called Stable Diffusion, which brought about a new way of generating images. So before diffusion models, there were GANs, which is generative adversarial networks, which were very popular for generating images, but they were like limited in their implementation to some extent. With Stable Diffusion, a new wave of explosion of generative AI came in place. Much of it also relates back to DALL-E, which is by OpenAI. But the problem with DALL-E is that it's a paid API and it's not an open source model which anyone can use. So the fact that these people made this model an open source model brings it about the power with anyone to control the generation process by themselves and fine-tune these models as well, which becomes very important. What happens with ControlNet is that when you generate images with Stable Diffusion, the way you do it is just you usually provide a input text, and basically the model understands that text and generates an image for you. But the problem is that the model is not great at understanding some things. So the model might be great at understanding facial features, for example, but the model is not probably good at understanding all the poses, for example, or let's say how many fingers are there in a human hand. That's a very major problem in Stable Diffusion models that everyone was struggling with. ControlNet is an implementation which just came around 1.5 months back, and it has been a game changer in this particular domain because it now allows us as developers to take more control of these diffusion models to generate images in different modularities and different forms. So just to get started with an example, here, as you can see on the first image, that's my original photo that was taken. And then the 3 photos are the images which are generated by Stable Diffusion. So the way it works and the reason it works is because of a module called ControlNet, which is an extra set of network, neural network, which goes alongside Stable Diffusion, and it allows to dictate basically the control process and the creativity within Stable Diffusion. So the way to control these is through different kind of models which are being trained via ControlNet method. So you can work with depth, you can work with pose, you can work with edge detection, and you can also work with scribbles. So the base idea is that it provides very fine-grained control over the generation process. Another thing is that, for example, depth models is something which is already available in Stable Diffusion 2 release. So there are different versions of Stable Diffusion models. So the first release was 1.4 and then 1.5, 2, and then I think 2.1 is also there. Most of the people and most of the community around is working with SD 1.5. Like we won't go into those reasons right now, but that's where 80% of the public community work is going towards. And the advantage of ControlNet is that this works for Stable Diffusion 1.5 models as well. Okay, and now also along with this, I'll share this PPT at the end for everyone to use. And the way to generate these images is also something which you can do for yourself without having any technical background about what Stable Diffusion is and what ControlNet is as well, because a lot of people are building open source UI on top of it, which makes all of this process easier and more accessible to anyone who wants to use these models as an art form without having to understand Python, even for that matter. You just need to run a command and you should be able to get this to this very easily. Right. So, for example, this link is where I'm attaching a Colab notebook, which is like a publicly hosted notebook, which everyone can execute on their own for free for most of the cases. And this is how the notebook looks like after it gets loaded. So this UI is called an automatic 1111 web UI repository. This is the most popular web UI, which is the ready-made web UI for using Stable Diffusion models. So the way it works is this is a text prompt where you just type in what you want to generate. And then hopefully if everything is connected and if everything is working together, it generates that output for you. So for example, let's say try. Okay, this is going to take a little bit of time. So we'll come back to it and see if it generated or not, because the reason that Colab might not work sometimes is because it's a free hosting which is provided by Google. If you use your own personal hostings, then obviously you get more determinism and consistent executions as well. Okay, before that, the entire talk from here on onwards is just about how do we use these models in different creative processes and in different photo editing and different image generation processes, right? So one of the advantages of ControlNet is, let's say if you use a canny, which is an sort of an edge detection kind of algorithm, like people in computer vision must be aware of it. And then depth is basically a 3D model kind of depth map, which is having the complete 3D representation of the source image. So here on the left-hand side is the source image. And then basically what we are trying to get the model to generate is, in the text prompt we are providing, generate a young man in a business suit wearing a black tie, wearing a black suit. And using that same pose, almost with the same look, it's able to generate a realistic photo of a human being, right? A little bit of sort of magic is there, to be honest, right? Because a lot of it depends on the fine-tuned model that you start with, and also a lot of it is depending on the quality of text you use to convey what you want the model to generate. So it depends on two things, right? So yeah, let's see. So this is the output and Apple, right? And like anyone can basically go and do it right now, right? You just need to click on that notebook, open in Colab, and you get this UI, and you just type this out and it will generate this for you, right? So this is Stable Diffusion 101 if you want to get started with Stable Diffusion, right? This is what you can do to start it. But as you can see, right, the quality of Apple is not realistic. It's not looking that good, right? Which means that there are two things which you can do. One is to change the base model which you are using to generate, which is like maybe it could be SD 1.4, SD 1.5, or any fine-tuned model that someone else has provided in open source community. Or it could be that you can provide more detailing in the text itself. So for example, you can change it to a green apple or a red apple, and it will automatically change to a green or a red apple, right? You can just say it's a basket of apple, and it will probably create a basket of apples, right? So it will depend on two things. One is the fine-tuned model, and the other one is the prompt itself, right? And the way the ControlNet extension is going to work is, I'll just give a very high-level overview. But the way the ControlNet extension is going to work is, you provide the reference image in this ControlNet dropdown here. And then from here, you just need to say enable ControlNet. And then in preprocessor, you choose what kind of preprocessors you want, right? So there are a lot of preprocessors, and a lot of this UI can look confusing. But just to begin with, canny, depth, what else? OpenPose. Yeah, these are the three main models to look at. And like we'll be covering most of them as well in this talk. And then the rest of the models are, you can explore later on. And every model has a very powerful flavor and the powerful method by which they allow the generation process control, as we'll see. Right, but this is how you can use this. So let's say you want to use OpenPose, and let's say you want to just use OpenPose. So just match OpenPose in both the dropdowns here, which says preprocessor and the model. So this is the model. Sorry, this is T2I adapter. We need to ControlNet OpenPose. Okay, so we need to use these two settings and just upload whatever image we want to give as a reference. So in this case, for example, it would be this image, right? And then we just write in the right prompt, and it will generate the right-hand side of image. So after the talk, obviously I'll share the slides and all the materials with you. So you'll find the prompt and the base model that I use to generate these images as well, so that you can reproduce these results on your own. So I'm not going into the details of prompt engineering and the model base, but everything is going to be embedded within this PNG file itself. That's another advantage of using automatic UI to generate images, because all the extra metadata in terms of how this image got created is already embedded in the PNG or JPG file itself. Okay, another interesting use case for depth that I found is that it allows for a lot of creative explorations. So for example, using a Coke bottle, I was able to generate a whiskey bottle, a cartoon rocket, and a steel Roman figurine. So as you can see, it's very much holding the shape as just like a cold drink bottle, right? And this basically means that now you can use any custom arbitrary shape, any real world shape, or let's say if you are working in Blender or any 3D tools, you can use those shapes from that angle and then nudge the model to generate anything which looks very photorealistic and which looks very real. So for any creative use case also, the depth model could be used. And like, as I said, right, the way to generate all of these is, let's say in the prompt, I would say that generate me a whiskey bottle. I'll upload the image of Coca-Cola in the ControlNet tab of the automatic UI and select depth as the preprocessor and the model, right? Just to confirm this again. So it will work for anything. It will create a depth map for it. It's as the first pass, and then it will use that depth map to nudge the generation process. So earlier, before ControlNet, what was happening is that there was no way to directly nudge the generation process. So now what we can do is give it a input and say that, okay, take this as the depth map and then use it for generation. Or if you, let's say, already have the depth map in a format, if you understand, then you can skip the pre-processing and directly say that, okay, this is the depth map that I'm giving you, or let's say this is the edge detection layout that I'm giving you. And then now you can use it to generate, let's say, apple, for example. And then the same image can be used to generate a watermelon as well, for example. So it will generate a watermelon, which will look like an apple because the base frame of reference looks like an apple. So that's the beauty of it. And these are the areas where we need to change from depth, like between what kind of inputs we want. So NERF is a completely different thing. NERF is basically a 3D rendering of the real world. So basically, if we take a screenshot from NERF and then we feed it into this model, we can generate anything from it. So NERF is as good as Blender output, but like it's completely different technology. NERF is about capturing real world information, 3D coordinates in a radiance fields. This is generative. This is to generate like 2D right now, but potentially 3D creatively in the future as well. Okay, another use case is for using Scribble to do creative exploration. So let's say, like again, I went very lazy here, but that's my drawing, as you can see, master artist on the right-hand side. And then I used it with two simple prompts, an ice cream and a bouquet of roses. So the same input, I can guide to generate an ice cream which looks that way and a bouquet of roses to look that way. If I do a banana or an apple, then also the model will try its best to put a banana or an apple in that shape. However, it might not look like a real world like banana or an apple because it doesn't conform to that shape. But the outputs are definitely interesting to try out and look at it creatively, right? So for example, you can create infinite number of food shapes by giving these kind of inputs. Okay, another example of depth model is what if different people acted in God of War. The first image is from God of War, Kratos. So again, very crude prompting, right? I did not pay a lot of attention to fine tune how a face looks like. It's very minimal 5-6 words description. So for example, this would probably be Virat Kohli dressed as a warrior. Lionel Messi in God of War. These kind of prompts are there. But as you can see, it generates quite realistic looking input following the same input pose. So as you can see on the shoulder pad and the armor, it tries to follow almost the same composition because we are using a depth map. The problem with this is, for example, in Virat Kohli's image, you can see that the model is trying to put a hand like this. And that's something which is unavoidable because the depth maps also are not 100% accurate depth map because they are generated or inferred from this image. So the model is getting confused, thinking that it might be a hand. That's why it's generating a hand there. But it definitely provides a good starting point to start looking at depth maps and then trying to control the process from there. Another use case is for interior design. For last month when we had a talk here, someone came and showed an interior design hackathon submission that they won in a big hackathon a couple of months back. And with ControlNet, this becomes very simpler because they had to do a lot of things to achieve those kind of things just 3 months back. And now what we can do is just give that depth map. So that one is, let's say, you can call it a Blender output or a depth map on the left-hand most side. And now you can generate different interior settings just by tweaking the inputs a little bit. So you provide this image, say depth, and then you say a futuristic Tron legacy style living room and you get the rightmost image. You say World of Warcraft or an orc style chair, then you get the center image. Everything made of bamboo furniture, then you get the left and most side chair. So that's how you can creatively keep the same form. And as you can see, all the images are looking very much identical. This was not possible without ControlNet. So let's say if you generate these images 4 times without ControlNet, without giving a reference, the model will generate good images, good outputs, but they won't be exactly similar to each other. So this is what one more advantage of using this model is. Another good exploration can come from using edge detection maps and Scribble to experiment with text styling as well. So all of these text styles basically are generated from Stable Diffusion again. So it can come in very handy to generate more variety of typography and good style text contents as well. So earlier, this was a limitation in Stable Diffusion models that it was not able to work on text. But now, because we are able to provide a structure to the model and provide guidance through that structure, we are able to work with text as well. And as some of you would have already guessed, since it works for text, it works for logos as well, and it works for any 2D image, which basically is a JPEG image. So as you can see that you can reimagine the Nike logo having New York City built around it. And I have also shared a couple of links which could be looked at, which are very good reimaginations along the same concept if you want to get more ideas in terms of how do you use this forward creatively. Another example for using canny/depth combination in ControlNet, you can use multiple ControlNet models together as well. So you can say that, okay, I want to use 20% canny, which is edge detection, and 80% of my depth model I want to use as a reference. So that sort of blending is also now possible since past 20-25 days. And it allows you for like using the same image as a reference and create very different outputs with very minimal efforts to preserve the same composition. Okay, and then, yeah, probably the last case for pose is virtual photo shoots. So with a technology called Dream Booth, you can basically have the model understand who you are as a person. And then you can say, okay, draw a picture of, let's say, Kartik holding hands. And you can give this pose image as a reference, which is also available through the same ControlNet extension there. And then it can generate an image doing the same pose. So with this, for a, let's say, human body generation, the opportunities are now endless because now you can take any reference image and have the final image generated in a very similar pose. So this opens a lot of interesting things as well, because before this, hands was something everyone was struggling with. And this opens a possibility that now, like almost picture perfect hands are, I would still not say pixel perfect, but very close you can get to real world drawing of hands. So basically, this all summarizes most of the things that we are going to basically now achieve through using ControlNet models using Stable Diffusion. And then I have added the links to the previous automatic UI and prompt engineering slides for people who are new. So you guys can attend to the previous meetups talk that we had around these so that you can get started with this automatic UI basically. And the way you type text here is, there is a fancy word called prompt engineering. It's just about telling the model what you want and having a good communication layer between the model. That's all there is to it. Yep. And then if you want to explore more, you can try variations of Dream Booth and ControlNet. That's something which I have not added right now. And then you can try and follow these two channels and areas to get more understanding in the field of the latest which goes in generative AI. For example, this YouTube channel, they'll have a video within 1 week in terms of any latest advancement that goes on. So that's probably the best way to stay updated. Yep, that's it. Any questions?
So, question number 8. So, like when the Stable Diffusion was trained, was it trained on DeepKlarity 3D images?
So Stable Diffusion 2, yes, but Stable Diffusion 1.5, the way it works is the basic add-on model which does the magic here is ControlNet. So this is an extension to Stable Diffusion. So let's say Stable Diffusion model is here, the ControlNet model sits parallelly on top of it, and then this model nudges the Stable Diffusion model with the depth understanding that it has been trained on. So your original weights are preserved, they don't get damaged, and a new model is learning how to control the depth, and then it's as an add-on adapter sort of thing. It controls any Stable Diffusion model. So just to answer your question with a little bit more clear imaging, the left-hand side is a standard Stable Diffusion block, and the way like this person is creatively achieved this breakthrough is that they trained an auxiliary model on the side for some time. So the advantage is that now the model on the right-hand side is a standard model. It could be plugged with any model on the left-hand side, allowing to get outputs with any of the 1,000 publicly available models out there without having to go through the entire training wheel. And this right-hand side models, these are specific models which are trained for edge detections, depths, and different kind of things using a controlled data set. And this is done with very minimal amount of training as well, because this was relatively easier for the model to train than the entire Stable Diffusion 1.5, which is on the entire Leon data set, basically. And the trick, again, is a little bit magical here. It uses zero convolutions at the beginning. That's the magic trick to get it working, because if you start with a certain amount of weights and bias, the model usually will not train and will disturb everything in the training. But this neat trick allows them to start from zero, where initially this model does not affect the output at all. And over time, with training slowly and slowly through gradient descent, it gets better and better at influencing the output through that depth map, for example.
So it is a student teacher.
No, it's a connected model. So it's an extension at runtime in inference. The input is being passed through here and here as well.
Yeah, but it's learning the instrument is learning the parameters of the weights from the Stable Diffusion.
No, ControlNet is learning how to use a depth map to get the exact same output. That's what this model is learning. Stable Diffusion is doing rest of the generative process. This one is about using edge detection or depth map. And then it's nudging Stable Diffusion to respect that depth map in a sense. But this is happening in real time. So let's say if you take 50 passes from zero to get that final image, then in all those 50 passes, ControlNet is active in that forward pass, and it sort of feeds it back into the Stable Diffusion at different layers and sort of nudges it that, okay, don't go this way because I want my chair to be exactly like this.
Using this for commercial applications.
Yeah, there are a lot of companies already out there which are using this for commercial use. So it allows for a very different variety of use cases. And like people are using to create virtual photo agencies. People are using to create product photo shoots. Using for game art creation, or a lot of different things people are using this for.
Something which is professional.
Yeah, a lot of people are earning money. Like there's a person called Levels.io. He's an famous indie hacker. He is at 25,000 MRR just for a photo AI editor tool using this technique, and they launched 1.5 months ago. Yeah. Sorry. Yeah, there is a segmentation model as well. I don't know where it. No, so you can basically use Scribble as an edge detection format as well, because Scribble is a sort of an edge detection preprocessor. What you can do is basically skip the canny edge detector. You can put in your own edge detections, and then you can feed it into the model. You just have to skip the pre-processing layer here. Okay. You can use anything. You can just remove the preprocessor which they have provided if you're not satisfied with their preprocessor, and you can add your own preprocessor. But that would require a little bit of coding to get the image to. Because canny is good enough. Canny is what everyone uses in a hello world example as well, because that's probably the most commonly used edge detection method that everyone is going to use. And it's very simple as well, because you just need to provide a low and a high threshold, and then based on that, it does a pass filter. And that's all there is. Like canny is just a fancy word for a high pass and a low pass filter, I think. So that's probably for the easiest one to use and add that as a pre-processing layer. But the idea is like this entire talk that I gave is more oriented towards, if let's say you are not familiar with the technical details, how do you get directly into it? But let's say if you are comfortable with the familiarity, you can actually go and fine-tune your Stable Diffusion as well. You can train your own model of variation of Stable Diffusion as well. Yeah.
So this
While automatic, is it available on device as well?
Yes. So
And right now you're showing it on Godawat.
yeah, because on MacBooks, it will cause a lot of heat ups with the studios and the live stream going in. But it can work on your MacBook M1 as well very efficiently.
So when I mean device like on, well,
So yeah, I covered that in the previous talk last one that I gave. There has been a little bit of work where these models are working on edge devices as well. The work is pretty much early, but for now, I think Apple has the more of the lead on that. But probably 1 year from now, Qualcomm has already done some tests, and they are also coming up with mobile execution versions of this. But the inference time is obviously going to be slow, and the quality is also slightly compromised because you have to trim down things a little bit. For example, when you do a floating point 32 to a 16-bit floating point, there is a slight reduction in performance, right? So here you need to even prune the model a little bit more to get it fit into the constraints. But let's say if you have a M2 iPad, I think like it will work smoothly there, and the Scribble model will give you a result in 10 to 12 seconds. That's the benchmark. Obviously, if you use online, you can get the results in 3 to 4 seconds, but 10 to 12 seconds is also pretty neat for a on-device application. But yeah, no guarantees on the heat ups. Yeah.
How is different from style transfer?
Neural, sorry,
Style transfer.
neural style transfer. So style transfer only applies to transferring the style, right? Here we are preserving the composition, not just the style. So yeah, you can say that, okay, for example, like in a sense, that is a style, but what essentially we are capturing is the way that item is formed in the 3D world, right? Style would be, for example, bamboo style. So that's the application of, let's say, neural style transfer. So any image you can give, and let's say apply a bamboo style to it. So that's something which Stable Diffusion already does a better job than the previous generation of models, which is like neural transfer models and some generative based models. But what essentially ControlNet is helping us to do is control the form and the shape of what we are trying to generate more than the style of what we want. So this is more about poses, the way I am holding my hand, the way I'm standing in front of a camera. Am I looking at the camera? Am I looking away from the camera? These kind of things is what ControlNet is good at.
Further questions we'll take, you can take them offline.
Yep. Okay. Good. Thank you.
Great. Thank you so much, Kartik. So now we will move on to the next talk. We have with us Pranay. Pranay is a lead data scientist at Freshworks. So let me just set things up here for a second, and we will get started. All right. Yeah, Pranay.
Thank you, Prakash. Okay. First of all, I would like to thank Akash, Sivakanth, and team at Jovian, Ananya, who invited me. It is great to feel to be here at Jovian. So today, my talk will be more or less overview of what kinds of problems do we solve using machine learning. So I won't be going into detail of the algorithms that we use in machine learning, but I will give a specific 2 or 3 different use cases and what do we do when we work as data scientists. Yeah, sure. Okay. So is my voice audible? Okay. All right. Okay, so quick introduction about myself. I am Pranay. I have been working in industry since 2018. So it is now roughly 5 years of experience. And I have worked till now in 3 different companies. So first was GE Healthcare. That was working with the healthcare imaging machines, CT scanner, MRI scanner. Then I joined ExxonMobil, which is in the business of oil. So there we worked with optimization of the plant that is running, which refines the oil. And then right now I'm working at Freshworks. So I'll give a very short overview of the different kinds of experiences that I have had and the kind of problems that I have seen during my stay in industry. So by training, I'm a physics PhD. So most of my studies have been in the realm of physics. So mathematics, pure physics. And then the part of the PhD quite a lot intersected with the mathematics that we have in machine learning. So that is how I made my switch. All right. So first thing that I would want to mention is, when do we use machine learning? So this took some time for me to realize that not every place we use machine learning. So if there are places where a science-based model or an engineering model is already available, we don't want to use machine learning. By the accuracy or the precision that these models have, that have been built over years, 400 years of research, they are far better than what we do with machine learning. But then why do we need machine learning? Because a lot of problems as we progress requires to tackle with hundreds of parameters. The parameters are so many that, and the modeling part is so difficult that using the traditional methods, it becomes almost impossible. So that is the point where statistics come into play. And when you start thinking in terms of statistics, that is the place where data science or the traditional classical machine learning models play a very important role. And slowly it is becoming a very important stepping stone for the entire humankind. So with that, let me start with a particular example. And the main focus of this particular talk, so the talk is not very long, it will be somewhere around 10-15 minutes. The focus is not going to be around algorithms, but one particular step of machine learning. So how machine learning exactly works? In the machine learning, there are 2 steps. One is we talk to business and we try to understand their problem, how do we want to solve it. And there comes in the first step of modeling. So the stakeholder or the business will come up with a problem. That problem will be very generic. Okay. Now from there, you have to map it onto a system which can be modeled, which can be used by machine learning models. These models are not going to understand the problem statement. They will understand tables, the tables which will have data, and data should be numeric. It cannot be any other thing. So all the calculations internally happen inside machine learning model. That always is the numeric data. So that is the first step, the modeling. And then the second step is the algorithmic optimization. So once you have modeled your work, once you take a particular problem and model it in terms of the data, which can be understood by the models, then there comes in the second step, which is you try different kinds of models. You try to make your features, optimize the features in such a way so that the model performs well, and you keep working to increase the accuracy. Now, there are different metrics. So accuracy, I don't mean accuracy in terms of the data science accuracy, the general, what we have understanding of accuracy. So precision, recall, whatever. All right. So today I will be explaining the first step. How do we model? So I will be presenting 2 or 3 different cases, and we will see how we go from a given use case to a place where we have modeled it. And once we have modeled it, the next step is to use these models, okay, the machine learning models. So let me start. This is one of the use cases that came up. So we might have certain documents. These documents can be PDF files, it can be documents, any text files, any format. Now, these documents we need to extract certain entities from that. So for example, if let's say these documents are rent agreements, so then we would want, say you have 100 rent agreements. So we would want a program to extract owner name, tenant name, what is the tenure, from what date the agreement starts and when will it end. All these things is something we would want. Why would we want this? Once we convert this unorganized data into organized data, then a lot of things can be done on top of this. So this becomes one of the layers on top of which other things can happen. Okay, we can run our SQL queries, we can do a lot of ETL, a lot of things can be done. So let's see, how do we convert this problem into a machine learning problem? So this is the modeling step, the most important step. Excuse me. Just I'll put it to silent. I'll continue. Okay, so this is the most important step. You take your documents and convert it to a form where you have your X variables, the variables which will be the input to the model, and then you have your Y variables. The Y variables will depend on the requirement of the stakeholders. So for example, a particular problem that we were faced with is there is a machine that is running and we want to predict when will it fail. Okay, so if you want to predict the number, when will it fail, the Y will become a real number. If you want to predict which component of the machine has failed, then let's say you have just 3 or 4 parts, then it becomes a classification problem. You have certain X variables, the running state of the machine, and then you have to decide on the Y variable what particular classification algorithm should give result to. Okay, looking at the data. So here we have certain documents, and then we want to convert these documents in such a way that it can be modeled. So how do we do this? One particular way. Now, each step in this process has a lot of variation, and that is where human ingenuity comes in. We spend our time trying to optimize each step of this process. So first is to extract the words. When you extract the words, you can decide what words to pick up, what words not to pick up. Then you can do a lot of pre-processing, stemming, lemmatization, a lot of things can be done. So that is the step where we choose what words are important for making a particular classification. Now here, in this particular case, what do we really want to do? We want to find out, let's say, owner. Let's start with 1. Okay. So by looking at all the words in the document, we want to find out whether a particular given word is owner's name or not. Okay. So it is more or less a named entity recognition, what is widely known in natural language processing. So we want to see the sentence, we want to see the words before it, the sentences after it, the words after it. And then we want to somehow create a signal for the model so that the model can look at these numbers. What numbers are these? Occurrences of certain words, or maybe importance of certain words. And it can make a classification. It can say that, okay, if these are the words before a particular name, then most probably this person is owner and the other person is a tenant. Okay. So we want to create such signals. So first we have to extract words. Then we have to create features out of this. So these features can be TF-IDF. It can be in the world of neural networks, it can be embeddings. Okay. Depending on how do you want to model it, these features will depend on the problem and how do you want to create your signal so that the machine learning model will recognize it. And then the third step is once you have found out, let's say after running this second step, what will happen is that these features will run and you will get what is called a NER, named entity recognition. So out of all the words you would have recognized, okay, these are the words which belong to a particular category or not belong to a particular category. So it might be so first step is to identify whether a given name is a person or not. Okay, that is a much easier problem to identify. Once you have identified that this is a person, then the next step is if you have multiple people in the document, then what is the relation between them? So this is another step or another widely used technique in NLP, which is identifying the relation. You have 2 people and you want to find out what is the relation between them. Okay. So for that also, again, you take these two people, and wherever these two names are occurring, you say, you take the words between them, and you can create features out of it. The simplest feature which you can think of is bag of words or the count vectorizer. So just count the number of words. But we can try to find out something much better than that. We can actually manually go through some of the documents and see what are the words that actually signal that, okay, if this word comes, then the word, the name before it is most probably a owner, and the name after it is a tenant. Okay. So these are the words that will, these are the things that we recognize and use them as features in our model. Once we have done that, the setup is there, and this setup then goes into a machine learning model. Okay. So is this clear? What will be the X variables? What will be the Y variables in our case? A lot of details are there, which I have not put it in the slides, but if anyone is interested, we can go into the details. So these are well-established methods: named entity recognition, relation identification. So the point is, from the words, from the documents, we went to numbers, and these numbers can help us in either classification or regression. Some kind of method which will help us in getting our job done. Okay. Before we move, is there any question? I will be changing the topic. I will be explaining some of the use cases. Okay, so these are some other use cases that I have dealt with in my previous 5 years of experiences. And I just give a short introduction or some summary as to how was the modeling performed. Okay, rest everything will be, and again, that this is just a surface. When we actually go into the depths of it, then there are a lot of details. So this is one of the problems at GE Healthcare. A machine was running. This can be a CT scanner or MRI scanner, and we had data corresponding to these machines. So logs will be generated by the machine, and the job was to look at these logs, and we had to predict which component of the machine has failed. Okay. So again, here the problem that was given was converted to a classification problem. We said that, okay, there will be only certain number of parts that we'll be able to identify. We cannot identify each and every part. Okay. And whatever parts we chose, for that some signal should be there in the data. If the data does not contain signal, by signal I mean there should be something special in the data, so that a very expert person at least will be able to look at the data and say, okay, most probably this particular component has failed. Okay. So this is one of the use cases where we took the machine data, and then we created certain features. These features were, again, some of them were the easy ones, the like count vectorizer, TF-IDF vectorizer, and some of the features were created by the help of subject matter experts. So we actually worked with the domain experts, people who build these machines, who wrote the programs behind that, those machines, the embedded systems. And we try to understand when a certain kind of logs is produced so that we can create certain features. So then in that case, these features will become certain numbers, which will be either very high when a particular component is going to fail, or either very low when a particular component is going to fail. So there were a lot of details, but the overall point is this data was converted into a numeric format, and then the Y variable became the different components, and then this was reduced to a classification problem. Okay. Another problem was that for a specific part, when will it fail? So let's say we have a lot of parts which are running. Can we take a particular part which is generating a lot of logs, and can we try to predict when will this machine fail? So this is another use case that a lot of companies have. And in fact, any machine which we do not want it to fail all of a sudden, okay, unplanned downtime, we do not want. This particular problem becomes very important. So here the logs were produced in our use case. The logs were produced by the machine. So we had a time series, and then at some point the machine would fail. Okay, that was the raw data. The modeling step was to take we had very few instances, so not all machines fail all the time. Okay, and especially these big machines, for a particular kind of failure, you won't have enough data all the time. So one of the step, the modeling step was here to convert it into a numerical form. The point at which the machine failed, we took that as the reference. Okay, subtract that time from the time that was written. So think of y as the time variable. Okay, and take this as the reference. Now this is -1 day, -2 day, -3 day, -4 day. So each y variable, each time variable will tell you that this much time is left. Okay, after 4 days, this machine is going to fail, or 3 days, this machine is going to fail. And the x variables were the parameters that was generated by machine. Okay, it can be current, voltage, temperature, whatever sensors are there. Okay. Now, once you do that, this problem is converted to a regression problem. So you take the data and do these ETL exercises. And once you have done this, it gets converted to a regression problem. Okay. Another problem that we were working on was in the oil industry. So here the plant was running and we had to optimize the plant. So we wanted to minimize the waste and maximize the efficiency. So again, the problem statement that comes from stakeholder is very different. He wants to optimize or maximize the efficiency. But how do we, as a data scientist, how do I maximize the efficiency? Okay. So again, there is a particular field where there are optimization scientists who can look at different variables and try to optimize it mathematically. But in this particular case, it turns out that the optimization scientists were unable to do so because of certain complexities of the problem. They had tried to create certain models. Now the thing is, when it came to us as data scientists, again, as I said, not all problems can be modeled. If you have a different model available, engineering model, or say there will be people at the plant who are chemical engineers. If they can model it, then that is the best way to go. Okay, because they know how the plant is working. But what happened in this particular case is that the number of parameters were huge, and there was no one particular model that could have predicted how to maximize the efficiency. Okay, so when it came to us, we said, okay, look at some certain parts of the plant and take in all the parameters that is going to affect this particular process. Okay, and then let's try to model it. Let's try to convert it to a regression problem. So let's say in a particular step of the chemical process, a certain waste is getting generated. Let's consider the quantity of waste that is being generated as the y variable. Okay, and whatever processes or the parameters that can affect this particular process, it may be a very weak signal. Let's consider that as the x variables. So we took that, we tried to model it. There were a lot of hiccups. In data science, nothing is obvious or straightforward. But ultimately, we had a model which could predict how much waste will be generated for a given parameter. Now, once you have this particular function, then you can try to see what if I minimize the waste. Okay, how should I change the parameters here so that the regression model would say that the waste is minimized. Okay, so that was the step, the modeling step in our use case. Right now, I'm working at Freshworks. Here, the problem that we are dealing with is demand forecasting. So certain number of so Freshworks creates a particular software that will help you in it is a ticketing software. So whenever the customers of Freshworks, they when they are serving customers, so for example, let's say you call Swiggy, then and you raise a complaint, then Swiggy will create a ticket for you. And once in 24 hours or 48 hours it gets resolved, then they will mark as resolved. They will refund or whatever is the resolution, they will do that. So this ticketing software is created by Freshworks. Now our job here is to do the forecasting. Let's say you have the data, past data, okay, and you want to look at the past data and tell your customers that, okay, in this particular month, how much tickets or how much demand can you observe? Okay, so then it creates a huge value addition to the company and to the customers. They can plan ahead of time how much resource they should hire. Okay, so demand forecasting is one of the I can say for at least manufacturing industry, it is one of the most important thing that they need. And the more accurate you are, the better is the reward for them. Okay, so here the idea is to again forecast demand. In this, we have tried what is called a time series modeling. So time series modeling here, in this case, time series modeling, the X variables are dependent on Y variables shifted in time. So basically your Y variable will be, let's say, the number of tickets that will be observed or the number of orders that will be observed. Okay, the X variables are the Y variables itself shifted in time. Okay, that is how a time series model behaves. What you want to do is you want to regress your present demand over the past. So the idea is, let's say we know by looking at the data, and you should have at least a few years of data. It cannot be just 1 year or 2 months of data. So if you have years and years of data, then in that case, you can try to regress. You can say that, okay, in the past, we have seen that in a certain month, the demand always goes up. Maybe there is a festival running, there is some special, something might be happening, which causes the demand to go up. And because of that, there are certain failures, the ticket volume increases. So you can try to predict the future by creating regression model on the past. You can say by looking at this particular time, the past time values, can I try to predict the future? Okay, so there the modeling step doesn't require other X values. If you have other X values, then a different modeling step can be created. But if you have just Y variable, you have just time, and in that you have forecasted values, then in that case, just take that and then run a time series model. Okay, and that is how you create a time series model which can help you in forecasting the demand. Okay, what else is there? Given certain query by customers. Okay, this is something in progress. So a customer, okay, this is in progress. We are working on it. So here I won't be able to give the modeling step. The problem statement is in a natural language, similar to what we have in ChatGPT. In natural language, a person can ask a question. Okay, the question can be fairly technical, like how much demand can I expect in next 1 week? Okay, and then some follow-up questions that let's say you get certain graph which shows, then you can ask what can be the minimum, what can be the maximum. All follow-up questions can be there. That will be based on the demand. And then in the natural language, from the natural language, we have to somehow semantically understand what the user is asking. And then we have to reply in the form of a chart or a widget, which they can interact with. So this is in progress. Yeah, this is pretty much all that I have. So was the idea clear that I was trying to convey? All right, that is all. Thank you. Any questions?
So, you know, first job, as you said, so how do you identify the which part of machine I get it, but what are the parameters for the failures? How do you identify that?
Yeah, so there are few of the parameters are obvious. For example, if there is a moving part and you have a measure how much current is being sent, okay, and how much acceleration do you see in that particular machine. So few of the parameters, if there are sensors, then they are obvious that you can take these values and try to feed into a machine learning model. All for all others, we have to sit with subject matter experts. They are the people who have designed the machines. They will be in a much better place to tell us what is it that we should be looking at. So often people ask that machine learning or data science is progressing so much. Will we have jobs in future? The answer to that is we will always have jobs in future, because no machine learning model can work on its own. The reason being, there are certain things that are designed in a particular way by the subject matter expert. A machine learning model cannot work on its own. You have to engineer your features in such a way that it can be recognized by the model. So for example, in one particular case, we were looking at some certain numbers that was being generated by machine, and we were trying to predict the y variable, which component or what time it will be failing. Now, when we met subject matter experts, they said that this number is not what you should be looking at. Convert this number to a hexadecimal representation. In that, there are certain bits that are important, and each bit has some meaning. Okay. So once we did that, the accuracy went up. So now, without the knowledge of subject matter expert, this is impossible. We could not have ever imagined. Okay. Any other thing? Any other question? Yes.
Are you able to establish causality of the variance?
That is a much more difficult thing. Yes.
Business user, they got a full sign.
Yes.
Business owners,
Hmm.
they will be looking at the component or what was the trigger point.
Yes.
Then rejection comes later, like next step, the actionability is the.
Yes. 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 So whenever we work on problems that are critical meaning something weird can happen and it can incur huge loss in dollar value, then we need to establish a causal relation. That is a much more difficult thing to do. A machine learning model will tell you that, okay, these are the features that are looking important and they are predicting this particular y variable in certain fashion. But to get into the causality, we have to reach out to subject matter experts. We have to talk to them. So that was one of the steps in one of the problems that we solved. When we created the machine learning model, we reached out to experts and we showed them certain graphs. And we showed that these are the trends that we are observing. So some of the trends, they straight away rejected, that this is just a matter of chance. Some of the things can just happen. If you take enough data, you can find a lot of chance events. Just because certain values went up and at the same time the machine failed, the model will predict that because of these values, this machine has failed. But it was just a matter of chance. So there, all the science or the engineering work comes into play. You have to talk to subject matter experts to make sure that whatever you are predicting, they are related. Causal relation is there. Data science will not give you causality, that is for sure, because all data science models are just looking at the data. The modeling behind it or the physics behind it is not something that we have fed into the model. If there is a way to feed it into the model, then maybe we can expect in future that it might establish or it might. So there is a part of machine learning which focuses on interpretable or what is it called? Explainable AI. Yes. So models should be transparent or at least a gray box. We should be able to understand what is it that they are predicting on. Okay. The more it is a black box, the more difficult it becomes to deploy it in a situation which is critical, where people can die, where huge dollar losses can be there. Okay. All right. Thank you.
Okay, well, so that was a great talk on how you looked at a bunch of applications of machine learning in the real world. So that was great. Next up, let us, we have a talk from Gopi Sivakanth, and Sivakanth is a researcher at Microsoft Research. And he would have been here in person, but he's currently in Hebbal, and you know how the traffic is. So we're doing this talk remotely. We hope to get him sometime in person as well. Sivakanth, are you around?
Yeah. So let me
Okay.
share my screen.
Perfect. You can share your screen and we can get into it.
Can you see my screen?
Yes, we can see your screen. Yeah, you can go ahead.
Okay, let me start this slideshow. Okay. Do you see it in big?
Yes.
Okay, great. Yep. Thanks for the invitation. I'm sorry that I can't be there in person. Yeah, because of the reasons that Akash said. But yeah, hopefully I'll see you sometime. So today I'll talk about, sorry, I'm Sivakanth Gopi. I'm a researcher in Microsoft Research. So I work in lots of areas of theoretical computer science, and recently I've been also looking at machine learning, specifically privacy preserving machine learning, which is what I'm going to talk about today. So let's dive in. So so the premise is that we have lots of data, and data is really important. They say the data is the new oil, and the biggest companies are the ones sitting on the most amount of data, right? Because especially now in their when AI models are getting better and better, the difference between companies ultimately might boil down to like the quality of the data that they have, right? So there are all these scaling laws for neural networks which show that to get better and better, you need more data. It's not just compute, but you also need more data. So you need both compute and data to get even better. So, data is really important. The only issue is that a lot of this data is private. So, so if you think of the public data, which is what we see publicly that everybody sees on the internet, is the tip of the iceberg. There's a lot more underneath, which is private, and that only these big companies have access to. So this and it's a lot of data, because I know this because I'm at Microsoft and I see huge amounts of data. They're never short on data. But the only issue for them, for most companies, is that this is private data and it's sensitive. So if you train a machine learning model on this private data and you release this model to do things, other things, there are major privacy risks. And I'll talk about what these risks are in a bit. And these risks are especially prevalent in large language models, because these are generative models, and they have this issue that they memorize verbatim whatever sometimes some of the training data they're trained on. So here is a fun example of like what can happen if your model memorizes a training example. So XKCD has this comic where a cop is trying to find some revolutionaries who are like plotting against the government, and what all the revolutionaries are communicating by email. So what he does, and Gmail trains their models, their autocomplete models on personal emails. So the cop is just like, long live the revolution, our next meeting will be at, and then he just presses tab to autocomplete, and then the Gmail client or any other email client is just autocompletes to, we are meeting at the docks at midnight on June 28th. So these are the sort of things that we want to prevent, that when you train these predictive models on personal data, there is such a chance. And this is not just a comic, this actually happens in practice, and people wrote papers. So there is this famous paper by Kartik et al. It's called the secret share paper, where they took this GPT-2 model, which is a large language model trained by OpenAI, and then they extracted a lot of private information from it. Like in this case, like you can get emails and phone numbers and whatnot of different kinds of people, which is not supposed to be there. And this is just an example, but technically GPT-2 was trained on things on the internet. But if you do the same thing with email data, then the same thing can happen. Like your bank account numbers and credit card numbers can come up here if you prompt GPT-2. So these are the sorts of issues that we see. And this paper, which did this attacks, also showed that there are lots of ad hoc ways to kind of stop this, and all these ad hoc privacy mitigation measures were not really working. And what really worked is this technique called differential private training, and which, though it's not perfect, but that seems like the best mitigation measure that we have to stop this kind of stuff. So let me tell you about what this differential privacy is. Any questions before I dive into that? Okay. Yeah, so feel free to stop me if you don't understand something. I don't need to finish everything that I prepared. So I think the most important thing that I want to communicate is the problem statement, and on what does this differential privacy mean, and the rest is like optional. Okay, so what is this differential privacy? So I'll spend a bit of time on the definition because I think that's the most important thing that most people should know. It's that, so if you have an algorithm, let's say it's a training algorithm, it's a machine learning model which takes some data and then outputs a model. So my algorithm is not the model itself, it's the training algorithm. Like for example, it can be SGD, stochastic gradient descent, or some other learning algorithm, convex optimization, some learning algorithm which looks at user data and outputs a model or some other output. So, and this algorithm, let's say it is a randomized algorithm, which means it's not always producing something fixed. So we say that this algorithm is epsilon differentially private if on neighboring databases, by which I mean that take a database and you change only one user's data in this database. So here, I don't know, maybe I should use a pointer. How do I get this pointer? Okay, so here, so this is, oops. Oh. Can you see this pointer or no? Anyway,
Yep.
so yeah, okay, yeah. So in this, so you have a model which is, and then you imagine it's a thought experiment where you imagine training it on two adjacent databases which only differ in a single user's record. So like here you can see that a single user's email was there in the input, and here the that user's email was not used during training. And then this training algorithm produces two models, model 1 and model 2. And now, you give an adversary access to these two models. You know, they can do inference, they can even look at the weights, and they can do all sorts of things. But then they were trying to find whether this particular user's email was used or not used. So they want to distinguish between these two cases. Whether, you know, if I give you one of these models at random to this adversary, they can't tell whether it was trained with this user's email or not. This is a very strong privacy protection, which means that if you can't even tell if the user's email was used in the training, it means that no personal information of this user can be there inside the model's weights or during its inference and so on. So that is the definition. So more formally, how do you say that these two models are hard to distinguish? So as I said, this training algorithm is a randomized algorithm. What it means is that what it outputs is not a deterministic single model. It outputs a distribution of models. And in general, we say that such an algorithm is epsilon differentially private if the distributions are epsilon close, by which I mean that if you take the ratio of probabilities that it outputs any particular model, the probabilities of the ratios is bounded by some constant e to the epsilon and lower bounded by e to the minus epsilon. So it's a measure of how close the probability distributions are. We're saying that on adjacent databases, the algorithm outputs very similar distribution of outputs. And obviously, the smaller the epsilon, the more private the algorithm is, which means that if epsilon is like 0, that means it's perfectly private. It's not even, you know, it doesn't matter whether this user's input is there or not. It's outputting the same distribution of models. And when the smaller the epsilon, the more private you are. And this definition has been, you know, introduced in theory in like 2006. And since then, it's been increasingly adopted, you know, in industry like Microsoft, Google, Facebook, Apple, IBM. They whenever they you know, train models on private data, they also include that you know, they do it using differential privacy, and they tell you, oh, it is we trained it with so and so, like epsilon equal to 1, epsilon equal to 2 differential privacy. Moreover, the US government also believes in this technology. So the latest US census, kind of like how we have a census in India, though they didn't have it, you know, for the past 3 years, but it's that every 10 years they do a census in US as well. All the census data has been released using differential privacy, because they also felt that the US government felt that there's lots of privacy risks if they just announce the census data without any privacy mitigation measures. Okay, so any questions about the definition itself?
Yeah, go ahead.
Yeah.
You can ask a question. There's a question, Sivakanth. I'll just
Oh,
get that.
sure.
So, as we've heard of one model known as CAT. So, in a generative adversary model, so there are two parts. One is an encoder and one is a decoder, right? An encoder basically produces an embedding based on our training data, right? So it is producing the encoding, and the decoder is basically doing the policing work. Basically, whether it is close to the ground truth levels or not. Here, are we doing the same thing?
So you're saying, I didn't understand your question. So here we are not talking about a specific algorithm like GAN. So I didn't understand your question. So GAN does this, right? I agree. So, you're trying to generate images which look like the training data. I don't understand the question exactly, but one thing is that GANs are also a particularly bad example of, how models can memorize training data, because a GAN can reproduce an image on which it has been trained. There are cases like.
So there's one, I guess the question, Sivakanth, is like, is there, so since you have this adversary here, is that like a similar to a decoder model? Like, is there an actual adversary?
I see. So yeah, that's a good question. So here we're talking about a hypothetical adversary in the sense that it's not instantiated with any particular adversary. We're saying that any adversary cannot distinguish. It's not even, we're not talking about a particular adversary that we don't want this particular adversary to distinguish. We're saying that we're proving mathematically. So you can say that it's an information theoretic lower bound, saying that no adversary can do it. So again, is a good way to do it, right? Like, you can train a model which gives, which takes these two things and then tries to distinguish. That's a good adversary, which might be able to distinguish. But I'm saying that, if I do this differentially private training, then even the best adversary cannot do, including GANs, which are good adversaries. Okay, so it's not it's an information theoretic bound saying that no one can do it, not just GANs.
So is it quite same to that? Like, is it quite same to what the encoder decoder does in a GAN? Like, let's say I'm not taking about image data, I'm talking about any data. Because in nowadays it doesn't care.
So, right. So GANs are a particular adversary, right? Where you're training a neural network. Here I'm saying, it's not even a neural network. It can be anything. It can be a supercomputer. It can be a quantum computer. It can be anything which is trying to distinguish these two, and it can't do it.
A mathematical impossibility, basically.
Yeah, exactly. It's a mathematically impossible to resolve. Yes. Okay. So, so let me tell you a little, recipe for how do you make, a differentially private algorithm. It's sort of a cookbook for DP algorithms. So it's actually pretty simple. Like there are complicated algorithms, but in most use cases, the algorithm is very simple. So it's a very simple recipe. So first, you limit individual user contributions to some small amount. You kind of say that nobody should try to influence my algorithm too much. So you try to limit it in some way. And then the really key part is need to use add noise to mask individual user contributions. Without adding noise, you can never make anything differentially private. As I said, if your algorithm has to be randomized, it has to introduce some stochasticity, some noise into the process to mask the process, to mask the individual user contributions. So these are the two main steps, and that's it. So you limit user contributions, add noise. So let me give you an example of how this recipe works. Let's say I have a simple problem. I have n people in a room and they want to compute their average salary in a private way. So nobody wants to reveal their their personal salary. And let's assume that they have like a trusted party who they trust, so they can communicate the whole thing. All they want to know is that average salary of everyone. Okay, so what differential, and we want to do this using differential privacy. So what differential privacy does is like you just compute an average and then you add some noise. And then you also assume that, each salary is bounded by some amount, let's say C. So C is the maximum salary. Nobody's earning more than let's say 1 crore per annum. And so that is your C. And then if somebody is earning more, you just truncate. So let's say these are anomalous people. So you just truncate and then you just assume that everybody have bounded salaries between 0 and 1 crore. And then you just average and you add noise, which is proportional to something called it's called a Laplace noise. So this is a particular noise distribution which comes up, which is specific to this differential privacy. So it has a particular density. Its density is like exponential in minus lambda times the absolute value of x. On the right, you can see a picture of how this distribution looks. It looks like, it has a peak at 0. So so basically you're just computing the true average. You first limit the user contributions, compute the true average, and add a little bit of noise. So now this noise makes it really hard for me to distinguish whether a particular, find a particular user's salary. Why is that? Because even if I know everybody else's salary, let's say I know the salary of everyone except X1, so what will I then know is X1 plus X1 over N plus C over N times some Laplace noise. I can multiply it by N. So what I know is X1 plus Laplace noise, right? It's like, and then I'm adding, multiplying the Laplace noise also by C. It means that even if this user salary is 0 or C, I cannot distinguish because I'm adding noise which is proportional to the maximum amount C. It's like if you have one noisy sample and you add, let's say Gaussian noise to it, you can't really know whether the signal is there or not because the signal gets damped, it gets swamped by the noise. So that is the intuition why it works. And you can prove mathematically this satisfies the definition I showed you. And that's where this particular distribution of noise comes in, because I want the ratio of probabilities to be bounded absolutely by e to the epsilon. This particular probability density will do the trick for me. So, okay, but the intuition is that you're just masking an individual user's contribution by noise. And the good thing here is that see that the noise scale also scales like 1 over n times some constant amount of noise, which means that if there are many users, the amount of noise that I need to add to make it private also goes down to 0. So as there are more and more users, I'll get more and more accurate estimate of the true average salary, but at the same time, I'm preserving everybody's privacy. Okay, so this is the general story with privacy. As you have more and more users, you can give them more and more privacy, and at the same time learn a general statistic or general trend more and more accurately. Okay, so that is the Laplace mechanism. So any questions about that?
Yeah, there's a question.
Sure.
Any? Sorry. Okay, so Sivakanth, the question is right. So is the question is is there a definite definition of small noise? Like how do you...
small noise. So here, I quantified the amount of noise that I need to add. It is like so Laplace 1 over epsilon has a particular noise distribution which scales like 1 over epsilon. And then I'm multiplying with C over N. C is the maximum salary and N is the number of users. So as N tends to infinity, this amount of noise that you need to add also goes to 0.
Yeah, so the question is, what is the value of epsilon over here? Or is that something you...
So the value of epsilon, that's a good question. So the value of epsilon is basically the amount of privacy that you're demanding. So the smaller epsilon means the more private you want, but then the cost of it is that you need to add more noise. So this is called the... So typically epsilon that people use is like 1 or 2.
Here, take epsilon value. Smaller, more private.
Yes.
What is the definition of this one? Can you give some context of that?
Yeah, so if I understand your question, you're asking that smaller the epsilon means more private. Now, what you're asking is, what is the definition of smaller? Okay. Okay. What is the definition of smaller in terms of epsilon? Like, are you asking for specific ranges or are you...
Yeah.
So yeah, so the general range of epsilon that is accepted in practice is about 1. Like anything less than 1 is very good privacy. And anything epsilon like 4 is reasonable, not very good, but reasonable privacy.
And any specific reason that we are using that lesson?
So any specific reason we're using the Laplacian, the Laplace mechanism for noise generation? Could it be anything else?
Yes, that's a good question. So if you want Laplace, this particular thing is needed to get the definition, epsilon differential privacy definition that I showed you. Then this is the best noise to add to get that particular definition. But even if you add Gaussian noise, you can't prove that it's epsilon differentially private, but there is a slight relaxation of it. It's called epsilon delta differentially private, and Gaussian noise satisfies that as well. So, and in general, people also use Gaussian noise, which is the most standard thing. I just showed this to you because the definition is easier. Yeah, so all kinds of noise work, as long as they have some nice properties. They need to have like converge very quickly to 0 and things like that.
Got it. Thanks. You continue.
So the other good thing about differential private algorithms is that they compose very well. So if you first, I think I have a picture here, it's better. So if you have a database and you have a machine learning algorithm and you train a machine model and you output it, and the first algorithm is epsilon 1 dp, and the second one you do it again, and then the second one is epsilon 2 to dp. Together, the total privacy loss you will face is just the sum of the epsilons. So this is a nice property of privacy, this differential privacy, that if you keep releasing information about a database using differential private algorithms, the privacy loss that you incur just adds up. Moreover, you can do it even adaptively, which means that the second algorithm can even look at the output of the first algorithm and then do something with it. And still, if the first and second are individually differentially private, the whole process is differentially private. Okay, and this is like, one of the nicest thing about differential privacy, that because, in general, this is what happens. It's not like you just train it once and it's over. You have lots of private data, you keep doing things with it. You train one model, you train another model, you learn something, you learn more things. So you want to understand how the total privacy loss is happening as you do the training more and more. Okay, so now let's talk about the specific context of private ML. So Akash, how much time do I have left?
Yeah, I think we have about 15 minutes.
Okay, great. That's a lot of time. So let's talk about private ML. So private ML. So what we want to do is, what you expect. So each user is giving, some example. Like let's say, let's take the example of maybe ads. So each person, you show them some ad and they click it or not, they don't click it. You can think of it as is Z, and Y is the ad you show them, and things like that. So this is the private information, or it can be like Y1 is an email that they wrote, and Z1 is like whether, or Z1 is the next word. So Y1 is like the prefix and Z1 is the next word in an email that they train. And then you want to train a machine learning algorithm which predicts Z given Y, right? So this is the standard thing. But here now you're assuming that each user is this input that you get from each user is a private information, and you want to protect this privacy of these users. And this is the general trend. Like, this is how all these tech companies collect data. They collect small amounts of data from millions and billions of users, and then they want to train a machine learning model which fits all this data that they observe across all these users. So learn a good model with, and specifically, in the goal. Clear thing. Okay. So specifically, machine learning models, the most common ones are, of course, deep learning models, because that is, where the world is heading. We want to train deep learning models using differential privacy as well, and that is like the biggest open question in this whole different area of differential privacy. Like, how do you do differentially private deep learning? So we want to add, as I said, the goal is to add some noise, to the weights, in some controlled way, so that the adversary cannot tell anything about the data that it was trained on by looking at the model. Like in particular, it can't tell whether particular user's data was used or not used by looking at the model. And in general, there's a cost to privacy. Privacy doesn't come for free. So, if you plot the accuracy versus the privacy loss, then it's, the more privacy loss you can incur, the more accurate it becomes. So this is called the privacy utility trade-off. So it's like, if you want to be really private, you have to face some loss in accuracy. But if you're okay with losing a little bit privacy, you can get more and more accuracy. And like as epsilon tends to infinity, you get the non-private accuracy, which is like when you train a non-private machine learning model on the same data, that's the epsilon equal to infinity. So there is this trade-off, and the goal of this whole area is to make this curve higher and higher. So, okay, so let me show you, this is the only promise this is the most technical slide of this talk, which is, how to actually make, so the, training of different deep learning models differentially private. Yeah, at least for the slide, I'm going to assume that you know how machine learning models are trained without privacy, which is this algorithm called stochastic gradient descent, and some variations of it like Adam and whatnot. But the basic algorithm, I hope that you know this, so which is that you have many examples and you want to minimize the loss function, which is the average of the loss over all these examples. So what you do in SGD is you sample a random batch from this set of examples, and then you calculate the average gradient. So the gradients of the loss function with respect to all the samples, and you average this gradients, and you get the average gradient across this batch. And then you take a descent step in the direction of this average gradient, right? And then so you update the weights. You do a gradient descent step. So this is the usual SGD. So now we want to make it private. And we are going to use the recipe that I showed you, which is that you first have to use limit user contributions, and then you need to add noise to mask user contributions. So because each gradient is computed on a particular user sample, it means that this is private information. Like the gradient is telling you some private information about this user. So you need to limit the user's contribution. So what we will do is we'll clip the norm of the gradient to some constant C. So if the norm is too big, it means that we're getting too much information from this user and we don't want to use all this information. So we clip it to have norm at most C. So this is the clip gradient step. So for each gradient, you clip it to norm at most C. And then we do the Laplace mechanism, which is to the average gradients, you're going to add some noise. And in this case, I'm going to add Gaussian noise. So, and then I do the gradient descent step. So it's pretty simple if you think about it. This is exactly the recipe I showed you. You just clip the user contributions and then add noise. But we are doing it to the gradients now. So this is called the DPSGD algorithm. It's a famous paper in 2016 by Abadi et al. It has like thousands and thousands of citations, but it's a pretty simple algorithm, and you can prove that it is differentially private. And there are already implementations of it. Like there is a pretty standard library called Opacus, which is built on PyTorch, which allows you to train differentially private models using differential privacy. So it's pretty simple. It's a few lines of code. You just load a model, and then you load an optimizer, and then you just give some hyperparameters, like, for example, what is the noise, that sigma that I need to add here? What is the clipping norm? How small should I clip my norms? And so on. Once you give these things, it'll output the epsilon, the differentially private parameter that your algorithm is satisfies, and I will also give you the final model that is trained. So you can try it out, and it works pretty well in practice. So, and one more trick that you can do is, like, we don't need to train our model. Let's say you want to train our model on private data, but then if you just start from scratch, you initiate your model with random weights, and then you start training, it doesn't do too well. Like you take a big hit in privacy, it's a big hit in accuracy because we're imposing privacy. But what happens is, especially now, we have this huge pre-trained models. Like if you go to Hugging Face, you can download like thousands and thousands of pre-trained models, which are really good and trained on large amounts of data. You start with this model and you assume that it's trained on public data. And now you can use DPSGD to fine tune it on your private data, which is very small. And then now you output your new model, which is like fine tuned on private data. It'll do much better than the public model, because now it knows the patterns of private data, but then it learned it using a differential private way. But still, it's much better than the public model in predicting the patterns in your private data. So this is the dominant regime. It's being used right now. And here I gave you an example of, like, some experiments from a paper we wrote, where we showed that these large language models do really well, even if you fine tune with differential privacy. So here is a benchmark. The model we trained is Roberta Large, and the top row here in this table shows non-private fine tuning. So you don't care about privacy, just train it the usual way on your private data, this is the accuracy you can get: 90, 96, 92, 94, 93. And if you do it with privacy, you still get pretty close. Like, instead of 90, you now get 87. Instead of 96, you get 95, and so on. But that's a reasonable cost, reasonable hit to take, because now you can actually show that this is a private way to do it. Like, the final model you're getting is not going to leak any individual user's privacy. And the same story also works with like image data. The non-private benchmark here is like, let's say it's 91% for ImageNet. If you do it with a differential privacy, you can still get pretty close, like 86, 85. And this is a paper from DeepMind. So yeah, so let me conclude. So I just want to say that differential privacy is a nice technology which lets you to train your machine learning models and private data and reduce privacy risks at the same time. And the state of the art is that you can get good privacy and nearly match the non-private training performance. So why not? And the theory is solid, and it also works empirically in practice, well empirically in stopping all kinds of privacy attacks which people tried empirically. So it's not just fancy math. It also works well in practice in stopping all kinds of attacks. So that I'll stop. Thanks.
Great. Are there any questions?
Slide where they're comparing the models, the text
Yeah.
models. Can you go back to that slide?
Yeah.
Epsilon was 0.7 or 6.7?
So, Sivakanth,
Sorry.
on the slide about text models,
Yeah.
Yeah. the epsilon is 6.7 here. So, sir,
That's true.
So,
I
sir,
mean,
question is that a very high epsilon?
so yeah, so I agree that so epsilon equal to 4 is something more reasonable. But so this is actually a very, it's a very good question, because it's also a very highly debated question. So what is the right epsilon to use? So mathematically, epsilon should be smaller than 1. Otherwise, it is not very meaningful, right? Like, if you just think about the definition and then look at the definition and what level of epsilon is providing me privacy, it should be something less than 1. But then what people observed in practice, because this is a mathematical definition, but then you can, let's say, somebody asked what happens if you train a GAN to distinguish these two. That's a particular attack, right? And people tried all kinds of attacks, like, and what is the best way to tell if a particular user's data is being used or not, or extract some secrets, some private data from the machine learning model that you train. So all these attacks kind of stop already at something like epsilon equal to 6 and epsilon equal to 7. So most of these attacks get pretty powerless when even at epsilon equal to 10, they stop working very well. So in that sense, like empirically, what people seen is that epsilon equal to 4, epsilon equal to 5, and 6 is also a reasonable guarantee of privacy. But mathematically, you want to choose something like epsilon equal to less than 1.
And if you reduce the epsilon here, the accuracy will go down.
Yeah, so the question is, if we reduce the epsilon here, the accuracy go down, and like,
Yes, it will go down. So you can see that in this picture, this is from DeepMind, where they trained a model to predict ImageNet labels of ImageNet. And you can see that as epsilon is growing, the accuracy grows. And when epsilon is small, there is a hit. So when epsilon is like 0.1, it is 77% versus the non-private is 91. And when an epsilon equal to 1, you see that it's at 84. So you see, this is the privacy versus utility trade-off curve that I wrote, like, which as epsilon increases, the accuracy that you have also increases.
and this is ImageNet trained from scratch.
No, this is ImageNet. I think this is ImageNet with pre-training.
Got it.
So on the left, you can see this is C410, which is trained from scratch.
Okay.
Yeah. And there you see that you take a big hit. Like, epsilon equal to 1, it's only 55%. Whereas we know that non-privately, you can get to 99% on C410.
Right.
So without pre-training, you take a really big hit. But with pre-training, the hit is pretty small. But then this trend is always there, that larger epsilon means more accuracy, but less privacy. So that is the cost. That's the trade-off for privacy and accuracy.
Got it. There's another question.
Can you go to mathematical points, right? Mathematical formula.
The Laplace.
Oh, the Laplace. Yeah.
You were saying that accuracy like nearly 100%, and then the epsilon value is 1.
Mhm.
Accuracy is vertical. Am I right?
When epsilon, no, so what is the question?
We said it there. I have seen it.
Yeah,
When the epsilon value is 1, 5, 1, 1, 1, and 2 is 8.
yes,
So actually, 1 was there in the chart.
Yes.
It was vertical.
yes.
But if you see if epsilon value will be the 1, epsilon is not going to contribute anything.
It's there, right? Laplacian.
Yeah, let us see there, but epsilon is not going to contribute.
No, so it is lap of 1 by epsilon. So if you increase epsilon, that reduces
Actually,
the,
that's one divided by 1. So epsilon is not contributing 1.
if you fix epsilon, yes.
Yeah. So how the accuracy getting?
Because C by N factor is multiplied with the
So because of the Laplace. Not because of the
1 by N is just adding standard C by N to everything. Yeah,
but there epsilon is not.
in the spatial case where it is not.
Yeah, when 1 is there, epsilon is not. Yes.
So is your question that like what happens if you pick epsilon equal to 1? Like
Right.
It means that if epsilon is 1, it is same as pretty non-public.
Yeah.
okay. So what does epsilon equal to 1 mean? Like at what point are we saying that epsilon has no impact?
Epsilon has no impact. What does that mean? So as I said, like larger the epsilon, the more private. Sorry, the less private it is. So like smaller epsilon means more private, and
Yeah.
So the number, any number that you adding and multiplying by 1.
Yeah.
Not going to contribute.
If epsilon is 1.
When the noise is increasing, that means the C by N directly coupling. So noise is more. Yes, their contribution is only noise, then no contribution. So I mean, if it is more, like
Yes, so when you actually do this experiment, what you do is you don't just pick epsilon equal to 1. You pick epsilon equal to 0.3, 0.5, 1, 3, 5, 7. You measure accuracy at each epsilon and then you report the results. So it's not that you just pick one and are done with it. Am I right in saying that, Sivakanth, that you
yeah,
try?
so you don't really try. It's basically a choice that you make. It's like
Okay.
how private you want. Let's say you want a privacy level of epsilon equal to 1, and then you just do this calculation and you just report it, and then you can you can tell how accurate this is, right? Like the error in your calculation of the true average will be of the order of C over n epsilon, because Laplace noise is roughly of the order of 1 over epsilon, which means like if you take the absolute value of this, its expected value will be around 1 over epsilon. So the error in your calculation will be C over n epsilon. So if you plot the error versus epsilon, it will be this curve. It's like as larger epsilon, you have lower and lower. Lower and lower errors. But when small epsilons, your error will be very high. So I can draw this picture. Maybe I think that will help. So I'm saying that if this is your epsilon, and this is your noise or error. This is kind of very hard to draw using this, but let's say this is error, then this is the curve that you will see. Oops. So this is the kind of curve you will see. This curve is basically C over n epsilon. Oh, I can do this maybe. Yeah, sorry. So this is my error, and this is epsilon. And the error is C over n epsilon, so this is the pattern you'll see. So this is the design choice you make. Okay, how much error can I tolerate and what is the privacy I need? Maybe this is a reasonable point. When I choose epsilon equal to 1, I'll get so much error, and then I do this.
Okay, there's one more question.
Mhm.
Two more. Okay.
So in the context of Sephardic, what is the legal definition of breach of privacy, for example? What is it that this model is?
Sorry, did I lose you?
So, hey, Sivakanth, can you hear us? Yeah, can you hear us?
Oh yeah, I can hear you. I think there's a momentary point. Yeah, I can hear you now.
In the context of CFAR 10,
Mhm.
what is the meaning of differential privacy? What are you protecting us from?
Oh, that's a good question. So it's an experimental result, right? So we are just saying that imagine that CFAR 10 was so imagine that CFAR 10 is a private data set where each image is a private, is coming from one user. And then we are protecting the user privacy in that case. So it's an experimental result where we're saying that suppose CFAR 10 was a private data set and each image was coming from one user, then what is the accuracy versus privacy trade-off? Does that answer your question? Like, of course, in real life, CFAR 10 is a public data set. And what happens is you apply these algorithms on real private data, where on people's emails, where like the data set is the email data set, where which you collected from users, from Gmail users or Outlook, and then you train a model.
So does that mean that like if you remove an image from CFAR 10, then an adversary will not be able to tell whether that model is trained with or without that image?
Exactly. Yes. Yeah.
Okay,
So I mean, this is actually non-trivial because, as I said, if you train a diffusion model, let's say, if you train a diffusion model on on images, let's say CFAR 10, and there is some particular image, or let's say you train a CFAR 10 diffusion model on personal images, then very likely that if you ask it, you can make it reproduce an image from the data set. Like, there are such attacks. There are some papers, like, for example, there is recently a paper which does this, like, how this reconstruction attacks for diffusion models, where like the model is able to reproduce, images which only appeared once in the data set.
Pawan, this is the last question.
So in the salary example, we don't have any bound on the individual salary for the patient. So like in real cases, won't that have any consequence? Say we are storing people's salary and we want to see the average, like the privacy algorithm is on the average, but the individual salary being stored, we don't know how much it's being burdened. Can be unbound. So like, does that have any consequence? Say, for example.
So sorry, can you repeat the question, Akash? The question is like, how good is this bounded assumption on salaries? Is that the question?
That's like what usually in applications there are
I lost you again.
things to want to query.
Yeah.
One is the average, the other thing is the individual salary.
Yeah.
So like you can create a differential private algorithm for say averages, but
Yes.
it should support other kinds of queries also.
Yeah. So the question is that in this particular case, you are able to find a differentially private average. But can it support other use cases?
For example, just getting an individual salary.
For example, just getting the individual salary.
Then that is about it, right? Like you don't know exactly at all.
Yes. So yeah, there is. So you cannot compute individual salaries because that is the gross violation of privacy. It just means there is no differential private algorithm
I mean, this is just an example. But what I'm saying is, like you have two different kinds of queries for performing it.
This is only an average model.
Like, but are there?
So you can call. This is just an example. You can find all kinds of statistics. You can find the median salary instead of the average salary. You can find the.
So would they be different models or would they be the same model? Is that your question?
What I'm saying is there are some set of queries which will still be differentially private.
Right.
Like if average is private, then
Some other will be.
some model or something will still be private.
Right.
So it seems like there was only like a certain set of queries which can be supported.
So is there a certain set of queries or a certain set of inferences that can be differentially private, or any inference whatsoever?
So, right. So basically the question is like, so there are certain statistics you can make it differentially private and still be accurate. But let's say you can basically theoretically, you can make any algorithm differentially private by adding enough noise. But the thing is, at some point, it'll become pretty useless. Like you're not really learning anything. It all looks like just noise. Let's say, for example, in this example, my goal is to learn the user one's salary. I mean, I can still make it differentially private by adding noise, which is C times Laplace 1 or epsilon. So there is no N here, which means the error in the salary is now C or epsilon. And the max salary is anyway C. So when epsilon is like 1, it's basically I'm not getting much information. I'm like adding C plus some noise, which is of the same order as the salary. And I'm getting, basically no information from it. So theoretically, you can make anything differentially private by adding enough noise. So all queries can be made differentially private. But then some queries you can make it differentially private without much cost to the accuracy, but some things you cannot. So it's always a trade-off between like accuracy versus privacy.
Okay. Great. So thanks a lot, Sivakanth. And can we have a round of applause?
Yep. Thanks. It was a great audience. Lots of questions.
Great. Thank you so much for joining. And yeah, so that's our third talk for today. Let me just turn this around quickly. All right, let's just turn on the light. Cool. Well, so those are all the talks we wanted to have today. I was also planning a talk, but then I think we had a good set of questions. I think maybe I'll do that in the next meetup. But I just want to say maybe a couple of things. One, there is pizza, so please stay for pizza. But also that since you've come here, I'm sure that you're really keen on learning data science, learning machine learning. And what I'd like to do is maybe, since we've covered a lot of technical material today, I'd like to maybe just share some tips on how you can actually take this back, how you can actually start making progress in your own journey, right? How many of you are already familiar with machine learning, are already using it in some form? Okay, some of you. How many of you are new or in the learning process? Any of you, right? Cool. So there's a good mix, and I'm sure everybody is at some spectrum here. And with so many new advances happening in machine learning, in artificial intelligence, you might wonder how exactly am I going to be able to keep up? So I just want to give you like a simple process that I try to follow to keep up with some of these things. So every month, you can try to do 3 things. The first thing is to learn something. So pick whatever you want to learn that month. And depending on where you are in that journey, you can pick, let's say, what is linear regression? That could be your goal for this month. Or maybe you've already learned about neural networks. Then what is stable diffusion? Or what is a large language model? So pick your goal for the month. And no matter how much time you have, maybe you have 2 hours in a day, maybe you have 2 hours in a week, maybe you have just 4 or 5 hours in the entire month. No matter how much time you have, figure out what you can learn about that topic in that time. So that's the first step. But then the second very important step, which I think a lot of people don't take, is to build something, right? So as Kartik showed today, you can start working with Stable Diffusion using just graphical user interface tools by running something. And then as Pranay showed today, you can take any kind of a data set and you can turn it into, try to turn it into numbers, try to find inputs, try to find targets and try to train a model around it. Or as Sivakanth talked about, you can try to apply differential privacy. So whatever you're learning, try to then build a project around anything small enough so that you can actually apply what you've learned. And then the third thing, and I think this is also very important, is to go out and share that with somebody. So put that project up on GitHub, share it on LinkedIn, create a short video about it. What that does is 2 things. One, when you have to share something, you have to get it to some level of completeness. It's not just that you're playing with it and just leaving it. You have to get it to a place where somebody else can understand what you've done. And second, you're also then that pushes you to get to a good result. And once you do that cycle, that this month, maybe first couple of weeks, you learned about Stable Diffusion, next couple of weeks, next 10 days or so, you try to work on a small project, no matter what time you had. And by the end of the month, you have released it, you've shared it online, you maybe put it on your resume because you want to get into a machine learning role. That cycle is a very powerful cycle because now every month you're making progress and now you don't have to learn everything. There's so much happening in AI that you simply cannot learn everything. But if you make this kind of progress for 6 months, you will feel a lot more confident, and you will be in a position where you will now be able to take that, show it to some company and maybe get an internship, maybe get a job, because what they're looking for is not whether you know every single thing in the world that exists, but what they're looking for is, do you understand fundamentals? Can you learn things quickly and go apply them to real world projects? Okay. So try to take that away. Whichever was your favorite talk today, try to apply it, try to build something and share it with us. So share it with your network, but also come share it with us. You have flyers to come join our WhatsApp community. So please go ahead, join them. We are going to have more meetups. We have webinars every week. So you can come subscribe to our YouTube channel for the webinars we're conducting. We have meetups every month. So just join our WhatsApp community, stay connected with us on Meetup. We'll get to know. We also have a bunch of courses on Jovian. And of course, if you're like really interested, you can come join one of our boot camps where we try to put this into practice, that you learn, you build, and then you kind of share and keep moving forward.